Greetings again, this is Scott, known as Cantaloupe to some online, and I'm continuing the 5-part series on how to create Platonic Solids in HTML5 Canvas. This is part 3 with the octahedron, following the cube and the tetrahedron done previously, and let's get right into it. So, what I want to mention in this video right off the bat is there's no single right or wrong way to create, really any kind of program. With respect to performance, there's some obvious concerns that need to be part of software design or game design or whatever you're working on, but there's many different ways to skin a cat, as they say. It's easy to confuse best practices with something that works. And they're not the same thing. So you might have an idea that nobody else has thought of. You might have a unique approach or an insight that is brand new, and that's perfectly fine, especially if it solves a problem in a way that hasn't been solved before. So, with that said, a lot of my solutions from one program to the next are variations on a theme, kind of. They're shooting from the hip is a way to say it. It's also improvisation, kind of coming up with a solution on the flies is what it's about. So in this case, I'm completely improvising. What you see right here with this function, I'm doing the same thing as I've done in the past 2 videos, and that is I commented out the last shape. The last one was the cube, so I just commented it out so there's no shape on the screen, and I'm creating a brand new function, and I'm not really drawing from anything but my vision of what needs to happen, and this is kind of a big piece of graphics programming, or graphics design, I guess, in general, is the ability to visualize what you want to happen and to think about how that can happen while you're doing it. So it's much more powerful to be able to craft a solution than to memorize a solution. It's that whole learning to fish versus being given a fish kind of thing. So in this case, what I'm doing is I'm imagining 4 points. It's an octahedron, right? So what do we know about polyhedrons, or Platonic solids specifically? We know that every facet is identical, and we also know that all of their points circumscribe a sphere, right? So they're all equidistant from the middle. If they're circumscribing a sphere, there's a middle point that is the exact same distance to every point in that shape. So this gives us kind of a real easy starting point to create any of these shapes. We already know that the points are equidistant from the middle, and so what I'm doing is I'm drawing 4 points around what will be the equator, I guess, of this shape, which is an octahedron. It's got 8 sides. They're triangles. They happen to be, I want to say they're equilateral. Yeah, they are equilateral triangles by definition. They have to be, because it's a Platonic solid, which means that all the sides and all the edges are exactly alike. So I'm going to start with 4 points, and then what I'm going to do is put a point above and below this perpendicular to the plane that is described by those 4 points. So imagine you have a flat plane and you draw a square on that flat plane, and then you tilt the plane and draw a point the same distance as each of those 4 points are from the middle, above and below, and then just connect them. And it's kind of all I'm doing here. So I'm just drawing a square with the same sine and cosine data generation process. It's called a generative. It's generating the data on the fly. And then I'm making an array of indices. So I'm visualizing the points as indices. So you can think about the 4 points of the square I just described as being 1, 2, 3, and 4. In computer science, you always start with 0, so it's actually 0, 1, 2, 3. And if you see what I'm going to do here in just a second, so I've generated that data with sine and cosine. It's a very short and simple thing to draw a square, right? And now I'm making this array, which is kind of a map. And then I need to add, so these are polygons. These are the indices of each of those points that are going to be turned into polygons. So you'll notice the first 4 lines on the screen right now are, they begin with the number 0. So that's the bottommost point. And then the last 4 lines begin with the number 1, but I'm about to change that to a 5. So as long as your order stays consistent, like how you're working with it, it doesn't make any difference what numbers you use. But what I did here is I pushed. I described previously how to push onto an array with the ellipsis. It's the expansion operator in JavaScript, and you can do that at the end of it, or you can do that very easily at the beginning of the array, which I've done here. I did both. So I pushed the top point at the beginning and the bottom point at the end, just for visual reference, just for an easy way to imagine this thing. I know that the first point is at the very bottom or the top, whichever way you're looking at it, and the last point is the opposite, and then the ones in the middle are the square on that plane in the middle. So it's just an easy way to organize it mentally, and then you loop through it, and you keep those points and that structure in mind, and you can kind of just make the code do what you're imagining. Imagination is powerful in this. So anyway, it's there's not going to be anything on the screen until it's all done, but you'll see it works, and it just kind of pops up at the end here. Again, with the drawing function, it's not being changed except for the color. We're dividing the spectrum, which is 360 degrees, in this color function call I'm using called HSLA. It's hue, saturation, luminosity, and alpha. 360 degrees is your color. So we're going to divide 360 by 5 because we have 5 shapes, and the end result, if you're looking at the intro and the extro of the video, we have 5 shapes, and we're going to end up with that, but they're each a different color in the spectrum. It spans the spectrum, and if you take 360 divided by 5 and then multiply it by the shape number, you get the proper color that it should be. So all that will be clear here in just a second. And something of note, the JavaScript map function is pretty handy. It's not the only way to process arrays. It doesn't do anything really super unique or special, except that it's compact, and it's a built-in feature of the array object in JavaScript. So it is beneficial to learn it and use it, because for brevity and consistency, it's super handy. But you can actually process an array, any JavaScript array, with a for loop or a for each loop. There's a lot of different ways to do the same thing, and not a huge amount of difference in performance, which is pretty cool for arrays. I mean, math, accessing, setting, reading data is super fast. You can do a lot of stuff really, really quickly in the Canvas API. Drawing tends to be the bottleneck. So you see I actually just got the shape completed, and it just popped up on the screen, and I'm happy when that happens. That's kind of like the reward, the cookie at the end, shooting the bullseye. Drawing tends to be the bottleneck in performance using it's called software rendering. If you're using GPU graphics, that's a whole separate subject, separate conversation. But I use almost exclusively software rendering, which means I don't use WebGL, I don't use shaders and stuff in my code. It's all just CPU, which some people don't particularly like, but I have my reasons, and I may go into that in a future video. Anyway, there's the shape we're going for, and I'm going to add the link and my contact, so enjoy, and I look forward to the next video, which will be a dodecahedron. Thank you.